Okay. All right. So for this one, we've got 2 blocks on a table, or one's on a table, I should say. Some coefficient of friction. This one is given as 5.1 kilograms, and it's on a pulley, and it's yanking down this 3.7 kilogram mass. Okay. And assuming the system starts from rest, when the masses have moved a distance of 0.38 meters, their speed is 1.32. And it wants to know the coefficient of friction and the magnitude of the tension in the cord. So we've got a couple free body diagrams we can draw here. So for the 5.1 kilogram mass, our tension goes this way, our friction goes this way, and I'm kind of at an angle there, so I'm just going to fix that. So for our 5.1 kilogram mass, our tension goes this way, our friction goes this way, we've got an mg and a surface normal. So in the y direction, really nothing's going on, but so it's not accelerating in the y direction, so that's 0. Our forces, though, are the normal minus mg, which means that which equals 0 from above. So then our normal is equal to mg. So that's all that gives us. Recalling that our friction force is our coefficient of friction times our normal, then that kind of solves for that for us. So in the x direction, our force is our tension minus our friction, which is tension minus mu n, which is equal to ma. Now, one thing we'll have to be careful of is to keep the directions of our masses, that our masses are traveling in the same direction. So that means for our 3.7 kilogram mass, we'll want our motion in this direction to be positive. So for our 3.7 kilogram mass, we would have mg and tension, but we want this to be our direction of positive travel. So in the y direction, our forces are mg minus tension. Although you might want to make tension positive because it's pointing up, we want to make sure everything's still in the same direction of travel. That way we don't have to worry about weird sign things. As this equals ma now. We don't need to worry about the x direction because there's no forces. And also because the systems are connected, these accelerations are going to be the same. And also the tensions themselves are going to be the same. We don't know the tension, but we do know a speed at a certain point. So let's use this equation of motion to solve for the tension, and then we can get our acceleration out. So from this, our tension is mg minus a, And I better be careful here. I should have been more careful throughout here, but I'm going to put 2's on these masses so I don't make a mistake. And I'm going to put 1's on these masses. As the question seems to give us that M2 is the mass on the table. Okay, so there's our tension there. And it should be with correct directionality. Or no, sorry, it won't be with correct directionality. So this tension will be, will come out to be a positive value, but we need to remember that it's in the negative direction, as we've already taken account of our directionality by giving it a negative sign. Okay, so with that value for our tension, we can plug that into our x equation for M2. So from M2 x, we have that tension minus mu n is M2a. And so then we have M1 G minus A minus mu n is equal to M2a. And now we can start to solve for our acceleration. As we have some of these quantities. Oh, sorry. That's just our equation that we can use to get for our mu, but we actually have more information because what we're told is that when the masses have moved a distance of 0.381, their speed is 1.32. So that means, how do I draw this here? So we've got 5.1 kilograms. $3.7. And so once we've moved a distance of 0.381 meters, our speed is given as 1.32 meters per second. And so we can apply some of our kinematic equations here. And now our acceleration is going to be constant. And so, and assuming we start from rest, then our xf is xi plus v naught t plus 1/2 a t squared. So if we start from rest, then that's 0. Start from 0, then that's 0. Then we can now solve for our acceleration. So our acceleration is going to be 2xf over t squared. But also, if we can use our velocity equation, so Vf is Vi plus At. Again, starting from rest, to say that our acceleration, or sorry, our time is Vf over A. And so we can plug this equation into this one to say that our acceleration is 2 times xf over Vf over A squared, which is 2xf A squared over Vf. Oh, I see. There's no point in doing it that way, I suppose. Okay, yeah, that's fine. 2xf a squared over vf. So then we can rearrange this equation now. So a is 2xf a squared over vf, just rewriting it. We can multiply out these guys and divide by a to get vf over 2xf is equal to a. Sorry, vf squared. Okay, and so now we have our velocity, vf in this case being at the point that it's given us here, so our acceleration is 1.32 meters per second squared over 2 times the distance traveled, so 0.381 meters. And so this comes to be 2.287 meters per second squared. Okay, so there's our acceleration at that point. So if we add that acceleration at that point, so we have our acceleration for our entire motion actually, sorry, because it's constant. So that's the acceleration that we expect. So now returning to our x kinematic equation, then we have m1 g minus a minus mu n equals m2a. So minus mu n equals m2a. And recall that our normal force is m2g. So then we've got m1 g minus a minus mu m2g equals m2a. So now dividing through by m2 and separating this out, we've got m1 over m2g minus m1 over m2g a minus mu g is equal to a. Bringing this to the other side, we've got m1g over m2 minus mu g is equal to a onto 1 plus m1 over m2. And we can actually divide through by g here and solve for mu. So then minus mu is equal to a over g, 1 plus m1 over m2, minus m1 over m2, or mu is equal to m1 over m2 minus a over g, 1 plus m1 over m2. And there we go. Finally, we have an expression for mu. So our mu is m1 being 3.7 kilogram mass minus our acceleration, which is 2.287 over g, which is 9.8 meters per second squared. Okay, and so working these values out, we get 72549 minus 367 times 0.72549. And so this all comes out to 0.32282. So then there is our coefficient of friction. Now, given our coefficient of friction, we can solve for our tension from either equation. So we could have actually solved for our tension from our M1 equation. So we had that the tension was M1G minus M1A, which is our 3.7 kilograms times 9.8 meters per second squared minus 2.287 meters per second squared, which comes out to be 27.798 newtons. So there's our tension from our M1 equation. We can also solve for it from our M2 equation, and it should be consistent. If it's not, then we've made a mistake. So from our M2 equation, we would have that our tension is M2 times our acceleration, 2.287 meters per second squared, plus our coefficient of friction times M2G, so 5.1 kilograms times 2.87 meters per second squared, plus 0.32282 times our mass times our acceleration due to gravity. And if we work this through, then we get 27.798 newtons. So that looks good. So they're consistent, meaning we did everything correctly. Or at least it seems to be. Okay, so let's check through the solution here. Okay, so we get 0.3226, so I believe that's the coefficient of friction. And acceleration of the system is A, which comes out to be 2.288, so that looks good. But then the tension comes out to be 31, which is strange. So the tension should be 5.7, so they used the wrong mass. Wrong mass to solve for tension at the end. Incorrect t-value. Alright. So they just used the wrong mass at the end, but that's